Thank you. So now we will have Michael Douglas, who will show us how to master n equals 1.
Thank you. So I'll be talking about work with a wide assortment of collaborators, and it's really trying more to put this into some larger setting. You got some flavor for what a lot of it is like from David Berenstein's talk with lots of arrows and X groups and things, and you might well be wondering what would induce a seemingly normal physicist to go so far in this direction. What prospects, are there for doing that? So that's what I'm going to try to, start putting some context around that. And I also, it will be very clear, I'm going to, have, be seriously influenced, especially at this point, by the recent, I think, very important work of Kummer and Vafa and collaborators. And in fact, my title you might recognize as a pun on some of the recent work. So we'll get to that. So, okay, so we can look back now, the second superstring revolution was a while ago, and have some feeling for what was accomplished and what was not. And certainly one of the very big things that was accomplished was that a lot of n equals 1 supersymmetric field theories, which really have the structure we would want for the supersymmetric standard model, were solved, starting with famous work of Seiberg and collaborators. And what solved means, of course, sort of has two aspects. And of course, the meat of it is that you really solve something and you compute superpotentials and lots of protected quantities. And then the other part of that statement is that you realize that there are some things that are too hard, but there are some questions that you can understand precisely without knowing them in detail, just knowing them qualitatively. And then in the case of n equals 1 supersymmetry, this really gets you exact results about the set of supersymmetric vacua, the domain walls, and so forth. So that's some very non-trivial stuff. And in some sense, the logical extension just of this success to cover string duality would be to just do the same thing for all the compactifications of string and M theory. Is there any fundamental obstacle to doing this someday? Well, obviously it seems very far in the future, but of course that's it may be closer than one thinks. Is there some fundamental obstacle to doing this, or is this the type of problem that we should approach in the same spirit? And of course, the same insight, the superpotential is protected. You should be able to get the vacua, is seemingly applicable here. And of course, when I say all, I'm just stating it in the most, not the best sounding form. Of course, we would be, in the present state of things, we know about some small fraction of the n equals 1 vacua clearly. We know some small fraction of what we should know. And obviously, any large increase in that would be very desirable. And so what kind of a description could you get? Well, obviously, it would be a very, very long list. We don't know if it's finite or infinite, but we might imagine some sort of a purely geometric reformulation of the problem. And I'll try to say what I mean by that, but I'll give as an analogy a statement which is not obviously false. I'm not sure. It's an interesting thing to try to decide whether it's true or false, but it's kind of in the ballpark. It seems to cover a lot. Is the statement that the n equals 2 four-dimensional, the n equals 2 four-dimensional compactifications are all dual to things that you can get by putting type 2b on a Calabi-Yau threefold. So you can look, and of course that's just one of the many families of constructions that were developed, but this one did seem to be kind of central in the developments, and other things like the heterotic string you could show were dual to this. There was some very large known set of Calabi-Yaus. The other constructions don't seem to be so broad. And crucial in 2b, the prepotential is really geometric. You just solve classical equations in principle to find a Calabi-Yau. You solve PDEs to get these theories and so forth, and you can really compute everything in terms of geometry as the mathematicians understand it. And then even if this is not literally true, there might be versions of this which are so close that you would want to count it as true in spirit. So for example, you might have to put in Calabi-Yaus with discrete torsion. Actually, there are interesting recent results that shows that in some cases these are dual to conventional Calabi-Yaus. So just the existence of another construction doesn't falsify this hypothesis, if it's dual to a standard Calabi-Yau. But let's suppose there's a discrete torsion Calabi-Yau, which is not. Well, if you could also develop the parallel geometric technology and claim it's differential equations with some little twists here and there, that's pretty geometric. That would count. And then, of course, that wouldn't give you a list. Nobody has this list of Calabi-Yau's to hand, but it'll certainly be some sort of landmark and target for future investigations. Some type of answer that you could give to this question now. Okay, so now there are a lot of candidate constructions of n equals 1, d equals 4. And there are some cases where you really do approach this point of getting a superpotential geometrically. So you'll hear some of this from Steve Giddings, Shamik Kaitru, but I think it's fair to say that once you even get the minimal level of complexity, like interesting matter and chiral fermions, that you would want to do real applications, at this point all the corrections bring in non-trivial instanton effects. And so we don't have a candidate n equals 1 construction that we could try to assign this central role to. But not having it, we can still formulate the hypothesis that there exists one. So I'll try to formulate this ultimate mirror symmetry hypothesis to say that, well, there is some object that we didn't precisely formulate yet. Maybe it's four folds with flux or some new kind of X structure that you're supposed to put on it. But to give it any content at all, we're going to say that it is something that a mathematician would recognize without having to sum infinite series of instantons. Maybe you can formulate a PDE that this thing is supposed to solve. Maybe you take the things that you get that way and you combine them, but in very simple and finite ways. I'll say, of course, an example of what I mean by that, why I put in that qualification. But in any case, you can state the construction in pretty standard mathematical terms, and then it really does turn out that these things are in one-to-one correspondence with n equals 1 compactifications. So I think that's a hypothesis one should entertain, and one might find evidence for or against not knowing the construction, and particularly if this hypothesis turned out to be false, which I think if I just randomly run around, and if I were giving this talk even a few months ago, I would say, well, this is probably false, but we should nevertheless put this hypothesis up there just to frame our thinking, because anything else is more complicated, so we should be sure that it's not this before we go on to these more complicated things. Okay, so I said a few months ago, and there really is recent important work that bears directly on this, of Vafa and company. And so to the extent that you can write down some string construction of an n equals 1 supersymmetric field theory and compute the superpotential by geometric methods, well, that clearly would seem to be evidence in favor of such a hypothesis. And so I'm going to have to come back to that. I'm just briefly quoting a few possibilities under better understood things. So there's this Gopakumar-Vafa duality that's been around for a while that says that you wrap d5 branes in 2b about a particular isolated S2, where that comes if you love the conifold. And then that's dual to the deformed conifold with flux. And then the flux superpotential is supposed to give you this gauge theory superpotential with instantons. And then that's a local construction, but there's nothing in the framework that says it can't work globally. And if it could work globally, then I believe with known constructions, such as, again, provided in work of Vafa and collaborators, Acharya et al., you might find examples where this works globally, unless you have examples. So that's a thing you could look for to get an example of this, which is important. So let's suppose you can do it for 5 branes. Okay, well, how far can this go? And well, the general starting point I want to take, again, to coming back to work with myself and my collaborators, is type 2b. And I think type 2b on Calabi-Yau 3 with branes and orientifolds. So type 1 is certainly a special case. More general orientifoldings, of course, is the closest thing we have as a candidate, but obviously not such a construction. And on the face of it, you have to add lots of d-instanton and worldsheet instanton corrections to this theory to get exact results. But what is true is that if you go to G string to 0, then you still have a formula for the classical superpotential that doesn't get corrections from worldsheet instantons. It is just a sum of two by now familiar terms, the holomorphic Chern-Simons action that comes out of much older work, the action whose variation is F20 equals 0, the condition for a holomorphic bundle living on one of these branes, and then the more recent Gukov-Vafa-Witten flux superpotential. So these are the NS and RR3 fluxes and the dilaton wedged into this. And then this is also an interesting source of superpotentials. And there's a certain sense in which this is even a special case of that. Once you've got the branes around, you can start moving them around in ways that create fluxes. But this does actually, this compact formula suitably interpreted and massaged and so forth, really does contain all the known type 2b classical superpotentials and type 1. And the simplest case would be, well, let's say type 1. We put in the Oriental folding. That's projecting some 2b gauge fields. That's a very minor, restriction of what you're talking about here. But the main step in getting something that most people would be willing to call a superpotential out of this is you pick some configuration to expand around. Of course, this is a priori written in terms of 10-dimensional gauge field, 6-dimensional, which is all internal. You have to identify the finitely many light degrees of freedom out of this following standard methods in this case, even in Schwarz-Witten, integrate out everything else, get a 4-dimensional superpotential. So as it stands, this guy contains everything, but it seems too abstract to be useful for anything. But it is the framework. And of course, this step you can make concrete in many, many different ways, some of which are familiar. I'm going to concentrate on a less familiar one, which is, again, what I've been working on quite a bit. So you can take the example of a C3 orbifold. So now you resolve that. You get a non-compact Calabi-Yau3. These are very familiar results at this point that you can realize in the first instance, what looks like branes that extending in 4 dimensions at points in this Calabi-Yau. But as you think about it, a very large class of things, fractional branes that wrap the various cycles of this resolved Calabi-Yau. It's not obvious that those are equivalent to these geometric branes wrapping cycles, but it's abundantly true. And it basically follows because all the structure of holomorphic branes wrapping cycles is holomorphic and doesn't care about the Kähler potential. And so you can see it even when you load the cycle back down to 0. And so the basic claim, which is more or less mathematics, in fact, this is really, you can trace through definitions, is that the standard cubic superpotential that you just get by projecting the n equals 4 theory to get this orbifold construction, which, again, I think is familiar to many of you, is a particular reduction of the holomorphic Chern-Simons action to this case. And in fact, this one kind of works the way, the simplest way it could, which is that there was a cubic interaction term in holomorphic Chern-Simons, and you pick some basis of these massless modes, you substitute in, you integrate over the manifold, and you get these A wedge A couplings precisely expressed as this. And then that really is precise. So that's showing that there are cases where you can be very concrete and you get out from something that looks cubic a cubic superpotential. But now, does this lead to the general prediction that the superpotential is always cubic? Since holomorphic Chern-Simons is always cubic. And the answer had better be no. That seems too simple for the real world. And in general, see, the simplicity of this answer was basically because you could truncate the massive modes. But of course, that's not, in general, what you would have to do. You would have this holomorphic Chern-Simons action, and you would just have to solve it perturbatively. Okay, so you would, more properly speaking, start with some reference configuration, F20 equals 0, and start perturbing around it. And then you have to systematically solve in perturbation theory. It's just classical perturbation theory, solving tree diagrams, but then those tree diagrams give you higher order terms into superpotential. There are examples of this in Witten's old work, and there is, in fact, a general theory of it if you look in the math and at this point in the physics literature, written now by Lazaroy, Tomasiello. And it falls into the framework of A-infinity algebras in the math literature. And there's a point, without going into any details of this, that this actually leads to an explanation, which is there in the literature. So the interesting point that you can see using this is that if you think about actually doing this process of solving this thing in perturbation theory to develop the superpotential, you have to choose a gauge. You got massless and massive modes, and you have to project out the massless guys. You're trying to get some effective action function of those massless guys and only integrate out the massive ones. And so you have to actually choose a projection. So in particular, you choose a gauge that allows you to write down propagators. And the only obvious choices of gauge, to say the least, are gauges that involve the metric and the Kähler data. And so there's a sort of a little paradox, which is that the superpotential is not supposed to depend on Kähler data. It just looks purely holomorphic. I was justifying previous comments, and there's various forms of the statement, but basically, how can it be that this purely holomorphic thing, to actually calculate it, you have to specify Kähler data? And it's true if you try to develop this thing in perturbation theory, but what you can prove without difficulty using these ideas is that two different choices of Kähler potential give you two different superpotentials that are related by essentially field redefinitions. So there's a generalization of field redefinition in this business, which is basically field redefinition plus integrating in and out. And this is in mathematics A infinity quasi-isomorphism. But physically, it's more or less what I said. And so you can see that it does depend. The specific expressions do depend on the Kähler class, but they effectively are related by field redefinitions, the answers that you get using this. So, okay, so could you do that in an example? Well, if you think about it, it's horribly complicated because doing perturbation theory on a Calabi-Yau requires knowing the Green's function on the Calabi-Yau. And you don't know the metric on the Calabi-Yau, and it's pretty awful. But you actually can achieve the same result by doing linear sigma model calculations. In fact, fairly trivial linear sigma model calculations. This is a result of mine with Govind Raja and Jay Raman and Tomasiella. So we looked at the linear sigma model of the famous quintic in P4. And I've spoken about this repeatedly at this point at the strings meetings. And you can think of this linear sigma model as Landau-Ginzburg-Orbifold C5 mod Z5 and treat it using orbifold techniques. And if it had been C5 mod Z5, you would follow a standard theory to say, well, there are 5 kinds of fractional branes. You get some world volume theory with a superpotential. You can discuss the point about whether all this is justified for 10-dimensional theory, but to this level it is. And so you get a nice theory of these branes, and the question is, what does it have to do with the branes and the bundles on the quintic that you might actually be interested in? And mathematically, there's a at least clear context in which this says, which is that you start with all the branes and bundles up here, and you restrict them to the quintic following well-defined geometry, but complicated geometry. Okay, but now how would you do that physically? Okay, well, physically, you start with the Landau-Ginzburg-Orbifold, and the main difference between the C5 mod Z5 and this thing is that you've got this world-sheet superpotential. And so you have to start computing using the world-sheet superpotential. And of course, the general thing you might compute in this theory, you have to flow down from C hat equals 5 to C hat equals 3. But it turns out for this superpotential, this topological quantity, you can calculate the successive corrections in the superpotential perturbatively. Basically, you can keep just the holomorphic piece of the superpotential, throw away the anti-holomorphic piece if this is all you're interested in. And there's a kind of very simple perturbation theory with correlators between these Volca operators and all possible boundary operators, these arrows. So this familiar orbifold cubic type superpotential admits a sextate correction, which is easy to compute. It has a systematic perturbation theory. It's perturbation theory, that's simpler than general perturbation theory. This is the point at which you see the complex structure of the quintic enter. And the claim is that brane world volume theory, suitably interpreted with this superpotential, which you could, in principle, compute exactly, reproduces all possible branes on the quintic. Okay, so that's interesting claim. Now, can one get a handle on that? Well, again, the context I would have to start talking about to explain what handle you can get is this A infinity algebra. So the original theory is related to A infinity algebra in some way. And in general, you can regard the superpotential as the generating function for structure constants. Higher ordered and cubic terms are higher order products in this framework. The higher order products are not associated, but they satisfy various nice axioms that you can write in various ways. One way is you can massage this a bit and show that the axioms are equivalent to the classical BV master equation. Okay, so there's an odd anti-bracket, and you solve this quadratic constraint. And once you have a description like this of the possible deformations, now you could ask the question, well, suppose I just had this. Suppose I didn't know physics. Well, how many possible deformations of this structure are possible? You can show on general grounds that the brane problem has to be one of these. We see these sextic ones explicitly. Is this some subset of the possibilities that are realized by Calabi-Yaus, or is this all of the possibilities? And it turns out that, in fact, they are all the possibilities, exactly. And you can use this to prove that this construction reproduces the derived category of coherent sheaves on the quintic. And this is a mathematical result of Paul Seidel. This is basically looking at the reduction of this to a calculation in Hochschild cohomology, and then you find you get exactly this number of deformations. I've stuck my name on here because we think we can prove that this is true for the topologically twisted Gepner model, so a more physical statement, but essentially of this result, that the topologically twisted boundary conditions in the topologically twisted Geppner model are objects in the derived category of coherent sheaves on the quintic, which you define at large volume. And then this goes back to originates in conjectures of Cavendish, as most of this stuff does. So, okay, so then I had to bring in the feared derived category. And that's for the usual reason, that you want to get some general result for the superpotential. And if you look at the details of how things vary in Kähler moduli, David explained some of this. You find that what are brains and what are anti-brains depends on Kähler moduli. So you have to lift up to some framework where you don't have to say what's a brain and what's an anti-brain. And then that's where you get simple results of this sort. And any result which is independent of Kähler moduli, and certainly superpotential, you would like to have that properties better formulated in that language. David told you something of the story of how you then make that more concrete by picking particular bases of brains. So an application, something I hope to do with this, I haven't gotten very far, is that, well, as I said, it's irritating that we don't know what most of the n equals and factifications are. Let's go back to this traditional heterotic construction where we try to make 3-generation bundles. Okay, so we specify all the term classes, including C3, 2 times number of generations. Well, in principle, using these ideas, you can just make it. You can make it as an object in a derived category. You can check to see if it's a bundle or a brain of some more complicated type. And physically, the idea is just, well, you take the known brain, D6 is carrying this tangent bundle, and you try to throw in some D0s, and they change C3. If you throw in 100 minus 6 D0s, I guess 200 minus 6, then you will get the desired bundle. And so the question is, does this combination of brains form a bound state? And that is the type of question which this formalism can partially answer and is leading up to. So the strongest solid result of this sort that I have is that using the type of basis I described from the Geppner model, this Valenson basis, you're looking for bound states. You can start decreasing the number of generations by multiples of 5. And you get bound states with multiplicities like that. And then you can show that for the cases where this makes sense, those configurations exist. Okay, and they are generically sheaves on P4 with point-like singularities off of Q. So assuming things are generic, they should restrict the bundles on Q. It's something, is it concrete enough you could check with enough pain? The main problem with what I've said here, well, you can only get down to 5 with this, 75 with this basis, because once this goes negative, you're in the situation that David described. You're supposed to do a Seiberg duality and get a related Seiberg dual theory and start looking for supersymmetric configurations in it. Presumably by doing that, you can lower the number of generations further. In this particular construction for the quintic, you get multiples of 5, but that's kind of specific to this example. It's easy to find examples where this is adjustable by units of 1. And so it's quite possible that once you have a construction which is general enough like this, you'll find that 3-generation models are pretty common. That most quintics have them. So that remains to be seen. So that's now, to come back to my previous framework, this is not geometric, but this is counting under the formulation of the thing that I gave. I should put that back up again to say that the ultimate mirror hypothesis of is to say we get things we can get by solving PDEs, bundles, and then we make some combinations of those. And then all the objects in this derived category, in principle, you can make as finite complexes out of bundles. Okay, so if you word things right here, I have left this framework of purely geometric things, but it is close enough that the mathematicians will recognize it. It's certainly counts to some people as geometry. And why does one need that? Well, again, this issue of combination of brains and anti-brains with putting in worldsheet instanton corrections. Okay, that's the thing which you've managed to sum up by mirror symmetry in this type of description. Okay, so we got to some description of classical. I've been saying A infinity and BV and not explaining because they're really kind of all things that are known on some level in physics, mostly appearing in open string field theory in the work of Zwiebach and others. If you could quantize topological open string field theory, you would get, in some sense, exact superpotentials. And you might try to phrase the more general quantum problem in that way. That brings us to this work of Vafa and collaborators, which you haven't even heard the half of, and so it's inappropriate for me to spend a lot of time on this. Hiroshi and Robert will talk about this, but there are very interesting examples where you can reduce holomorphic Chern-Simons theory of these brains to a finite dimensional, even matrix integral, and compute everything using standard large N techniques for the, in the large N limit, the solution actually reduces to being expressed in terms of a master field for these matrices. So you reproduce earlier conjectures of Kummerer and collaborators that you reproduce quantum effects by a deformation of a classical geometry. So it's very relevant to this type of hypothesis, to say the least. There's a lot of non-trivial things. As I said, these talks haven't even come yet. And so let me not try to dwell on that. But I'll just say that I think that the question of whether this is evidence for or against this hypothesis in the way I phrased it, really, to the extent you can get results in the superpotential from a master field, from a classical solution of a large M problem, then they really do seem to be evidence. Now, a priori, if you take n finite number n brains, this is a quantum integral over an n by n matrix. And that's a quantum problem. If you look at the known solutions for matrix theory, they're not geometric in the sense I tried to phrase it on the previous slide. So you'd like to know whether you can get the finite n results that you need for a compactification with finite n brains out of master fields or large N. So that's certainly a central, I think, question in at least addressing the hypothesis I described. If you then go on to try to do it for compactifications, you face the question of whether these simple reductions from 6 or 3, depending on how you count, dimensional holomorphic Chern-Simons theory in general has such simple reductions. That would be amazing, but, we'll see. And then another issue that you should address, if I have time, is the fact that, I don't, you'd like to phrase a version of this that that takes into account the fact that the closed strings are dynamical. So I'll explain that to you in private if you're interested, and stop there.
Yes, do we have any questions? Greg Moore.
Greg Moore from Rutgers. You mentioned that you might be able to reduce everything to Calabi-Yau fourfolds with X structure.
That's the
I take it X is unknown.
Well, that's right. If I had a conjecture, I would present it.
Could you speculate on what kind of thing you imagine X would be?
Well, as I said, I think the most important clue in this direction is in the work of, don't point it this way, is in the work of Vafa and collaborators. And so to the extent you have geometric duals to Calabi-Yau 3 with flux, then Calabi-Yau 3 with flux in brains might be the answer. But time will tell. I mean, I think it's an important question even in the absence of a candidate, because it could turn out to be false. And you should still know
that. Steve Giddings, Santa Barbara. One of the morals of these flux compactification stories and generalizations thereof is that the underlying manifold is not necessarily Calabi-Yau. When you take into account the string coupling, you can get sort of more complicated geometries and so on. So you're conjecturing all of that is subsumed in this kind of construction?
Well, when you say things like warped Calabi-Yau, or you want
well,
all sorts of other constructions.
Yeah, okay, but
You found a class to which the other things are dual. I mean, that could also be false.
Well, for example, G2 is a natural analog of Calabi-Yau in higher dimensions, in a sense. Right. But it sort of looks like there are things that are even more general in that, say, they don't have Ritchie flatness and so on. You have more.
Calabi-Yau in string theory is not Ritchie flat.
Okay.
There is this more technical sense. See, we're only asking to compute n equals 1 protected things. We're not even asking to compute the Kähler potential at this point. So the question is, yes, for computing the superpotential, is it a Calabi-Yau? And so, for example, you don't
Okay.
care whether it's Ricci flat or not, a priori for that question.
But it could be a more general geometry, certainly.
This is a falsifiable
Yeah.
hypothesis. I mean, that's why it's worth saying.
Okay, thanks.
It's over to you.
Michael Dine, Santa Cruz. In your introductory remarks, you sort of implied you might hope to make some statements about non-protected quantities, some qualitative statements. Could you say a word or two about your hopes for that?
Yeah, I have a few more slides about that. The basic, so the basic thing I would say about that is that you should really, to get a well-posed problem, okay, you should be counting Minkowski and ADS vacua, okay, for various reasons, even phenomenological ones. Assuming you're just trying to find supersymmetric vacua, a priori, an ADS vacuum with small negative cosmological constant is as close to our world as a flat supersymmetric vacuum. So you should count them both. The ADS vacuum would depend on the Kähler potential. You can define a sort of modified Witten index that nevertheless counts them with signs in a way that doesn't depend on the Kähler potential. So that's the sort of topological quantity that I would hope to get at with these topological considerations.